every material expands, or rather it can expand or contract due to change in the temperature. So when the temperature rises, it is going to expand, and if it contracts, then the temperature falls. It is established that change in length delta L is directly proportional to the length of the member and temperature. So delta L is proportional to length and temperature. If I want to remove the constant of proportionality, which is this, then I have to put a constant, and that constant is called as alpha, which is nothing but coefficient of thermal expansion. So now I need to define the coefficient of thermal expansion, which is change in unit length of material due to unit change in temperature. Let us move further. You can see this bar. Previously I told you that if the temperature increases, then the change in the body is going to take place. So if this bar is going to go through the change in temperature, then you can see the expansion of the bar is taking place. Every material expands when temperature rises. If the expansion is freely permitted, you can see here there is no obstruction given. There is a free permission for bar to expand. So if the member is freely permitted, no temperature stresses are induced in the material. But if the obstruction like this will be given over here, then some stresses will be introduced. Thermal stress. Just like direct stress or shear stress, there is a concept of thermal stress, which is if there is a change in temperature of a body, then thermal stress is going to act. Let us see how. With increase in temperature, material expands, and with decrease in temperature, it contracts. If free expansion or contraction is prevented, then the stress will be generated, and that stress is called as the thermal stress. We will see two cases. The first one is if free expansion is fully prevented, and if the free expansion is partially prevented. Let us start with the first case. Free expansion is prevented fully. You can see here the expansion is prevented fully, right? There is no gap for expansion of the bar due to change in the temperature. Now, previous slides we have discussed delta L is coefficient of expansion alpha, length and temperature. If I divide both the sides by L, then we already know linear strain, that is epsilon, is delta L upon L. L will get cancelled on this side, so it will become alpha T. If I put the value of linear strain in modulus of elasticity, then finally I'll get the value of stress, which is alpha into T into E, which is the coefficient of expansion into temperature into modulus of elasticity. So this value is called as thermal stress. Moving to the case 2, you can see here there is a gap which is given. So it is not fully prevented, it is partially prevented. So there is going to be a gap for the expansion of this block. Let us put down into the formulas. So delta L is alpha TL minus this gap, which is delta, again dividing by length both the sides. So linear strain is delta L upon L, and if I divide by L over here, and by simplification I'll get this value as epsilon is alpha T minus deformation divided by L. Again putting that value into the formula of modulus of elasticity and doing the simplification, I'll get the value of thermal stress, which is alpha T minus deformation divided by L into modulus of elasticity. While doing this, you would have noticed the formula of thermal strain also. This is the formula for thermal strain, when the partially permission was not given. It was fully permitted, and this is the formula for the stress when the partial permission was given for the block to move. Both the formulas are again written over here, right, when the thermal strain is found out. So I can again define thermal strain as change in length due to change in temperature divided by the original length. So this was the concept of thermal stress.